Welcome everybody. My name is Marton Terucik and my presentation will be about smart tags. Smart tags are mainly for indoor localization, so that's their main purpose. All right. There are several RFID localization systems. Normally, they are mainly use the reader side, so the reader tries to localize a RFID tag. The RFID tag is mainly passive. It's just a normal tag and has not so much intelligence. Yes, they use inexpensive conventional tags and the generated localization data is retained on the reader side. That's what we call smart reader network, where we put the intelligence on the readers and put the localization logic on them. And there are our new method called the smart tag, which we put some logic into the tag. It will be a complex tag because its original specification, it will have much more logic. So that will be a more complex tag than it was done before. And the location data will be generated inside the tag, so it will know where it is. And it can share the information with the readers or other infrastructure like Wi-Fi or smartphones or PCs. And we can use a hybrid technology where we combine the smart readers with smart tags. Most applications use RSSI information. RSSI means Receive Signal Strength Indicator, and this information mainly means distance. So the receive power is decreasing with distance on a logarithmic scale, and this distance information is then used for triangulation or trilateralization. These are the most used applications. That's the most frequent used ones. Right. And they try to locate the tag from the reader side, as I said before. But that lacks a lot of raw information because the information that the reader supplies is a RSSI, which means a data that is átlagolt for other measurements, and that's not a raw data. But if we can get the raw data, the receive power, we can use it for much more precise localization. And that's because the reader tries to locate the tag in that situation. The electromagnetic wave have to travel to the tag and travel it backwards. So it's decreasing not on second order, but on first order. So it will be much, much smaller than when it left the reader. All right. The smart tag method is a inside-out version of the standard methods because the tag does the localization and the other signal processing. The tag should or must know the reference coordinate system, so it can calculate its position in that system and should know where the readers are separated from each other. Yes. We can use some topologies. The main topologies is fixed readers in a room, for example, like in the corners, or it can be in a building, much further away from the cells. All right, and the tags are moving, and they receive the transmitted data. But it could be reversed, so there could be active tags in the corners and moving readers. But it's more complicated and it's much more expensive. So we have to distinguish the readers from each other, so they have to transmit their unique ID in order to distinguish them. So it can be put in the existing protocol. So there are ways to put that information in the existing UHF protocol. All right, and we have a solution for this smart tag. We created a new hardware. We named it Black Forest. It's a very complex hardware. It can receive the raw data and it can process it in order to get this RSS information, which is the raw signal strength. Right. And so if you get this information, we can use experimental localization methods. We can analyze them and develop some localization algorithms. I use this device technically wise. It communicates in the UHF ISM band, the same frequency as the RFID readers. IQ information is accessible, which is good for demodulation and getting the signal strengths in a much more easy way. It can transmit in the same way as a RFID reader would, so it can imitate RFID readers. These are some modulation types: PPSK, FSK, ASK, binary phase shift keying, frequency shift keying, and amplitude shift keying. But the most RFID readers use amplitude shift keying. All right, it receive mode. It can listen to several channels simultaneously. We use the frequency division multiplex, so each reader would communicate on a specified frequency. So not in time division like with a normal reader. Yes. And it has some inertial sensors like gyroscope and accelerometer, which can be used for more precise localization where RF information is not ready. All right. It can communicate with a PC through USB port. And the baseband information is available on audio outputs, so it can be processed with a normal sound card. All right, this is the device. These are the main blocks, like power, USB, microcontroller, baseband signal conditioning, the RF amplifier, and the BPSK modulation, demodulation, and the gyroscope. And these are the ready-made hardwares. Yes, they can be a transmitter and a receiver, not in the same time, but it can be pre-selectable which function they will serve. As we can see, that's the USB cable, and these are the audio cables going through an audio card. And yes, it has two antenna ports, one receive port and one transmit port. So it depends on which function we use. We can put that antenna to the right port. All right, and inertial information. Yes, for higher spatial and temporal quality of RFID localization, transponders have to be extended with sensors that can measure relative displacement and rotation of the tag between RF localization measurements, where they are not covered by readers. So, like inertial sensors, accelerometer, gyroscope, and magnetometer can help in this localization. And it's useful when we know where are the person or the receiver facing, which antennas should it see most. There can be models put on this localization scheme. All right, so we made measurements, so much measurements. Here are one. This is the received power versus the distance. At 0 meter, we can see it transmits at minus 20 dBm, and with distance, it decreases. This is the elméleti elvárt received power, and this is the measured one. It can be seen that it's similar to it, so we did well. But wait, there's more. There's a new device which can process the signal on itself. So it has an ADC converter, and the signal processing is done on it. It has a DSP processor, so there's no need for external computational sources. It can receive with 4 separate antennas, so it can look in 4 directions, and it can store the measured data on an SD card and can communicate with Wi-Fi and Bluetooth module. And it has an ADC, which is 24 bits, 2-channel stereo for the I and Q information. It's a delta sigma modulator and use 64 times hour sampling. It's just the technical information, and it can use external sensor nodes, which can be used for the recording the body movements of the wearer of this device. And it's battery operated, so it don't have to use power outlets and cables. It is under development, and it is named Snowflake. It's its alias code. All right, this is the block diagram of it. It uses almost the same blocks, power USB microcontroller and others, and but it uses more inertial sensors, and here are the communication devices and the SD card. Right. And here are the new topology. We can see it uses 4 separate antennas, and it can communicate with the Wi-Fi and Bluetooth. All right, in conclusion, Black Forest works perfectly. It is proven in the practical scene, and several measurements were made by it. But the new version will help much more in defining more precise localization algorithms thanks to its advanced design.